3.2 exponential and logistic modeling. So the one note thing in this section, exponential population model. If a population P is changing at a constant percentage constant percentage rate R each year, then P of T equals P sub 0 times 1 plus R raised to the T, where P sub 0 is the initial population, R is expressed as a decimal, so they'll give it to you as a percent, so you'll need to make it a decimal, and T is time in years. All right, tell whether the function is exponential growth or exponential decay and find the constant percentage rate of growth or decay. So number 2, P of T equals 4.3 times 1.018 raised to the T. So following this model that we have up here, P sub 0 is 4.3. This number that's being raised to the T is 1 plus R. So 1 plus R equals 1.018. So I need to subtract 1 from that. So R is 0.018. Now, because this number is greater than 0, it is exponential growth, or it is an exponential growth function. So therefore, exponential growth function, can't spell, my goodness, with a growth rate of 1.8%. So we take the decimal that we get and we make it into a percent, and then that tells us either the growth rate or the decay rate for the function. Number 6, G of T equals 43 times 0.05 raised to the T. So what's P0? 43. Now, 1 plus R is 0.05. So what is R? Negative 0.95. This number is less than 0. So what is this? Yep. So this is an exponential decay function. I don't have negative what? Negative what? 0.05 minus 1. This is an exponential decay function with a decay rate of 95%. Okay, so if it's negative, that tells us that it's decay. So it's a decay rate of 95%. We don't say a decay rate of negative 95%. Okay, decay rate implies that it's negative. All right, determine the exponential function that satisfies the given conditions. So number 8 tells us we have an initial value of 52, and it's increasing at a rate of 2.3% per day.
Sets, like to like chapter 14 notes, there should be 2 of each because it's for stats.
Yeah.
All that. Thank you. My stapler's up here if you want to use that. What'd you say, Lily?
Would it be f of x equals 52 in parentheses 1 plus 0.0.023 to the power of p?
Yep. So initial value is P0. So that's 52. R as a decimal is 0.023. And we know that what goes in there is 1 plus that. So 1 plus R is 1 plus 0.023. So we'll combine that together. So setting this up, P of T equals 52 times, in parentheses, 1.023 raised to the T. And that would be our function. Is this a growth or decay function? Growth. Let's see, number 10. We have an initial value equal to 5, and it is decreasing at a rate of 0.59% per week. All right, so P0 is 5. Then R is what? Yep, 0.0059. Because it was already a decimal, it's a percent, but I needed to move the decimal over to get it actually as a decimal. No, because T is just time. So like when we're actually solving problems, yes, but like the setup is, nothing is different. So then, now, it was decreasing, so what does that mean this number needs to be? Negative. So I'm going to do this like this. So then I'm going to add the 1. So negative 0.0059 plus 1.
So it would be 0.994.
Yep. So then P of T equals 5 times 0.9941 raised to the T. these are out of order. We're just going to do this stuff in order, and I'll go back to that. All right, number 16. These ones are a little different. Initial population is 250, and it is doubling every 7.5 hours. So, our P0 is 250. Now, what's different about this one is the fact that it is doubling every 7.5 hours. What did they not give us in this one? Yeah, a rate is a percent, right? Now, they're telling us that it's doubling, so in a sense, that kind of is our rate. It just looks a little different. So, yeah, so it's just going to be 2, but nothing's being, like, added to it, okay? Because we don't have, like, a percent that's changing. It's just, we know that every single 7.5 hours, it is doubling. So, then we have every 7.5 hours. So, that is going to be like dividing. So, okay, hold on.
So would it be like 2 in the parentheses to the power of 7.5t?
So that's a common like mistake that happens. So it's actually going to be like
T over.
T over 7.5 because it's doubling every 7.5 hours. So basically we have to do the time divided by 7.5 to figure out what is happening. This will make more sense when we do like legit word problems with these, when you see it like actually coming into play, because it just looks a little bit weird when you're trying to like write it out like this right now. So this is P of T equals 250 times 2 raised to the T over 7.5. And just for reference, in case any of the ones that you have in your homework look like this, the book writes this as 250 times 2 to the 2t over 15 because they don't want a decimal up in the like exponent. But I would just write it as t over 7.5 to not be confusing. But either one would be the same. They equal the same thing. All right, 18, same kind of thing as 16, but a little bit different. So 16 was doubling. 18 says that we have an initial mass of 17 grams. And this is a weird word, halving, I don't know, halving, once every 32 hours. So initial mass, so P0 is 17. So doubling was 2. What do you think this one's going to be?
1/2.
Yep, 1/2. And every 32 hours, any idea how I will write that one?
Would it be T over 32?
Yep, T over 32. Now, I'm going to show you 2 different ways to write this one also that are both acceptable. But first of all, we'll just use this information. So P of T equals 17 times 1/2. Make sure you put that in parentheses, raised to the T over 32. the way the book will write this, or as like another option for how they'll write it, is P of t equals 17 times 2 to the negative t over 32. Why are they able to do that?
Because you just work it out, it would just flip the 2.
Yep. So you can just, basically it leaves it the same as 16. It just is telling you that this is a decay problem. This still is a decay problem because it's halving, but it just is a way to like show it a little bit differently than the 1/2. So I would take either on a quiz or a test if you wrote it either way. And if for some reason I mark it wrong and you're like, well, this is what I had, just sometimes if I have one thing written on my paper, I don't always catch the other, even though I'm like looking at them to try to see. So, anyways, all right. Let's look at a couple word problems with this. So this one's not a like specific problem in the book, just an example. Suppose a culture of 100 bacteria is put into a petri dish and the culture doubles every hour. Predict when the number of bacteria will be 350,000. All right, so we know that we start with 100 bacteria, so P0 equals 100. We know that it doubles every hour, and we're trying to find out at what point we'll have 350,000 bacteria. Okay, so to set up this equation, I want to walk us through kind of what's happening. So at hour 0, so when it starts, there are 100 bacteria. At hour 1, it has doubled, so how many bacteria are there? 200. At hour 2, it has doubled again, so how many do we have? 400. And let's do one more. At hour 3, it's doubled, and what do we have? 800. So I'm trying to figure out how to write an equation that is going to show what's happening without me having to go through here and count, okay, at hour 4 it's 1600 and so on and so forth, because all the way out to 350,000, that wouldn't be very fun. But we can write an equation that will find that for us. So we know that our initial value is 100. So I'm just going to work with the first one for right now. So we could say this is 100 times 2 to the first. Okay, it's doubling every hour, so that's kind of going back to number 16. That's why I was looking to see. Sometimes I do the example like this one before I do these two. So it doubles every hour. Down here, the next one, 100 times 2 squared. So how can I generically write this as P of t equals something? Raised to the t. So 100 times 2 raised to the t. So this would be my generic equation. Now, P of t is after how much time we have however many bacteria. So they want us to find the amount of time. So we're going to plug this 3,500 in for P of t. So, or I don't know why I said 3,500, 350,000 equals 100 times 2 to the t. So divide by 100, that takes off 2 zeros, so now we have 3,500. I was just predicting the future. Equals raised to the t. Now, I know that we didn't have a ton of time to spend on logarithms last year in Algebra 2, and so that's why I kind of hate that they do this section before they do some of the later stuff in this chapter, because I feel like it needs to be flipped for you to know how to solve. But anyways, so I rewrite this as 2 to the t equals 3,500 like this, because when I solve a logarithm, because this is exponential, to solve for t, I need to undo it using a logarithm. So I use the finding the L method. So this would be log base 2 of 3,500 equals t. Do y'all remember sort of kind of doing this very briefly? Okay. So on your calculator, I'm going to remind you how to put this in your calculator and solve, because obviously it's been a while, and like I said, we didn't spend a ton of time on it. So over here on the left we have math button, so hit math, and I would arrow up because you'll get there a lot faster. You're looking for option A, which says log base. So remember, the log button on your calculator is for base 10. So if you want something other than base 10, which in this case we have base 2, we need log base. And then you just fill it in. So this little box is going to be the 2. The bigger box in the parentheses is the 3,500. And then you just hit enter.
Wait, you hit math, you said?
Yeah, and then arrow up to log base. So t equals 11.77, and that is in hours because we were told that it doubles every hour, so that's where the t part comes into play. This is hours. Now, do you know what 0.77 of an hour is? No. Good answer. Are you stuck, Tristan?
Yeah, I don't think my calculator has
Okay, so if your
They,
calculator doesn't have that, then you're going to have to use the cheat code to do it. Which is annoying, but it's fine. Is you have to use the change of age formula.
it. Oh, yeah, I think I did it last.
Which would be log of 3,500 over the log of 2.
You said 11.77 of an hour or just 0.77?
11.77 hours. Like, hours, yeah. Tristan, when we take the quiz or test, if you want to use mine to not have to do it that way, you can use my calculator for that. Huh?
Mine's the same way. I remember last year it said it.
Oh yeah. Well, maybe we can get somebody in another class. Or Riley, do you have your calculator? Maybe somebody can borrow Riley's and somebody can use mine then. All right, so I want to know, so 11.77 hours is a sufficient way to write that, but let's say they wanted to know exactly what it is, then we would take the 0.77 hours, so 0.77 of an hour, and we multiply that by 60, and when I do that, I would get that is 46 minutes. So I could then say, to officially answer the question, predict how long it's going to take or when that's going to hit, it would be at 11 hours and 46 minutes. We would have that amount of bacteria.
So do you want us to write it like that on quizzes and stuff?
I'll take it either way. It kind of depends on how the question asks. If it wants to know an exact time, then I would say rewrite it, but more so the book writes it this way. I usually just leave it. Let's see. I'm gonna do another example here. So that was bacteria growth, but another really common thing we use exponentials for is half-life. So suppose the half-life of a certain radioactive substance is 20 days, and there are 5 grams present initially. Find the time when there will be 1 gram of the substance remaining. All right, so, all right, so T is time in days. Okay, because it's talking about 20 days here. So we know we're dealing with days. We initially have 5 grams. So P0 is 5 grams. Or just 5, I guess I could say. So this is half-life, so I would say most of the time they write it as like 2 to the negative something. So this would be negative T over 20 if I'm writing it as 2. So this would essentially be the number of half-lives. So setting this up, I would get P0, or not P0, what am I doing? P of T equals 5 times 2 to the negative T over 20. And I want to know how long it's going to take so that there's only 1 gram left. So I set this up. 1 equals 5 times 2 to the negative T over 20. So I'm going to divide by 5. I'm going to go ahead and swap it so I can set up my log without having to write an extra step. So 2 to the negative T over 20 equals 1/5. So to do the log, I make the L. So this is log base 2 of 1/5 equals negative T over 20. Now, negative T over 20, I'm basically multiplying by negative 20 to get the whole answer. So negative 20 times the log base 2 of 1/5 is going to be equal to T. And then I can plug that in. So if you want, you can do it all as one big thing, or you can do it in steps. So negative 20 times math, arrow up to log base 2 and 1/5. So we would get that T is equal to 46.44 days. I'm going to do another one like this one, but I'm going to have y'all try to kind of tell me like everything that I need to put in so you can make sure that we're understanding. All right. 34. So this is another word problem. I'm going to try to not write the whole thing out and just give you relevant information. The half-life of a certain radioactive substance is 65 days. There are 3.5 grams present initially. And so they do this question in like parts instead of this last one was all written as one question. They do like a part A and a part B. So part A wants us to say how much of the substance is remaining as a function of time t. So let's do that and then I'll write part B. So, what do I know? Yep, P0 is 3.5.
Time is in days.
Yep, time is in days. And you don't necessarily have to write that, but it's beneficial so that when you're putting your units on at the end, you don't have to try to go back and figure that out. How would I be writing this part?
2 negative t over 65.
Yep. So then how do I write the function, like the whole function all together? Like P of t equals what?
2.5 times 2t. So negative c over 65.
Yep. So this is officially the answer to this part here.
Would you put the 2 in parentheses or does it matter?
If it's just a 2, you don't really need to. I mean, if you want to, that's fine. I usually just do that when it's half because you have to remember that that exponent's going on both pieces. So that's why I do it. But if you just want to for consistency, you can. All right, so then part B wants to know when will there be less than 1 gram remaining. So we take our equation and we're going to set it equal to 1. I know it says less than 1 gram, but if you find out when there's 1 gram remaining, anytime after that is going to be, there's less than that. So 1, actually, I'm going to write the 1 on the other side so I don't have to flip my whole equation. 3.5 times 2 to the negative t over 65 equals 1. So divide by 3.5, 2 to the negative t over 65 equals 1 over 3.5. And I usually just leave this until I get all the way into plugging it in my log so that it can just deal with it. So how do I write my log that I'm using to solve?
Log 2. 1 divided by 3.5 equals negative t over 65.
Yep. And then I can take and go ahead and multiply by negative 65 so that I'm just left with t over here. So negative 65 log base 2 of 1 over 3.5 equals t. We can plug that in. Keep hitting the wrong button. So when I do that, I get that t is 117.48 days. So anytime after that, basically, I know that there is less than 1 gram remaining. But this is the answer that they're looking for when they say that. All right, any questions about that? All right, problems for this section. And what I'm going to do is you don't have a ton of time left today, so I'm going to give you probably 25 minutes tomorrow at the start to work on these as well. 1, 5, 7, 9, 13, 15, 17, 31 and 33. So, and we'll see where we're at tomorrow too. Like, if after 25 minutes, if y'all are still working and not done, like, I'm flexible to give you more time, but I also don't want us just wasting time. So.